Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 8 on the special right triangles. This is our final lesson within the unit on right triangle trigonometry, although it doesn't have as many connections to right triangle trigonometry as it will to the wider branch of trigonometry as you move forward. But we want to introduce what are known as the special right triangles in this course so that you can use them more as you transition into Algebra 2 and deepen your understanding of trigonometry. So let's get right into it. All right, the isosceles right triangle. This is going to be the first one we look at today. Now, there are two right triangles that arise frequently enough that they require specific study. We first begin with an isosceles right triangle, also known as the 45-45 right triangle. Let's take a look. Exercise number 1. An isosceles right triangle is shown below whose legs have lengths of 5. Letter A. Why must the two acute angles both have measures of 45 degrees? All right, so why is it that this angle and this angle both must measure 45 degrees? And otherwise, why do we call this a 45-45 right triangle as opposed to just an isosceles right triangle, which wouldn't be incorrect? Pause the video now and think about this for a second. All right, well, it's pretty simple, right? Because these two sides are congruent, right, then these two angles must be congruent, okay? And since the two acute angles of any right triangle must add up to 90 degrees, and they're equal, right, then they must both be 45. So first, the two acute angles must be equal and must sum to 90 degrees, so each must be 45 degrees. So that's just a name that they give to isosceles right triangles. All right. Now, again, primarily what we're trying to understand with both this special right triangle and what's the second one to come is simply how the three side lengths relate to each other, what they, quote, look like. So, obviously in a 45-45 right triangle, the two legs are equal in length. The question is, how does the hypotenuse relate to it? Let's take a look at that in letter B. Use the Pythagorean theorem to determine the length of the hypotenuse in simplest radical form. Okay, great. So why don't you go ahead and use the Pythagorean theorem, not right triangle trig, but the Pythagorean theorem to figure out the length of AC in simplest radical form. Pause the video now and go ahead and take a few minutes to do that. All right, let's do it. So let me say, 5 squared plus 5 squared is equal to c squared. That's going to be 25 plus 25 is equal to c squared. C squared is going to be equal to 50. I can take the square root of both sides. So c will be the square root of 50. Now I want to write that in simplest radical form, which will boil down to the square root of 25 times the square root of 2. Square root of 25 is 5, and root 2 I need to leave as root 2. So we will put that right there. All right, that's it. No big deal, right? But let's see if we can develop a pattern now that we can exploit every time we see an isosceles right triangle. All right, exercise number 2. For each 45-45 right triangle shown below, determine the length of its hypotenuse in simplest radical form. Awesome. Well, why don't you go ahead and do this now for letter A and letter B. Exactly what we did before, we're just looking for the length of the hypotenuse in each case. Pause the video now and go ahead and do both A and B. All right, let's do it. So in this case, we'll have 3 squared plus 3 squared is equal to c squared. All right, that's going to be 9 plus 9 is equal to c squared. C squared is equal to 18. Take the square root of both sides. C is the square root of 18, which we can then break into the square root of 9 times the square root of 2. And C will be 3 times the square root of 2. I tried to trick you a little bit here by laying the right triangle on its hypotenuse, but of course that doesn't particularly matter, right? We could then take this thing and say 10 squared plus 10 squared is equal to c squared. 100 plus 100 is equal to c squared. Give myself a little more room. 200 is equal to c squared, and c is equal to the square root of 200, which I can then break into the square root of 100 times the square root of 2. Square root of 100 is 10, and I leave square root of 2 on its own. All right, so that's going to be 10 square root of 2. Now, hopefully, you're starting to say to yourself, I think I see a pattern. Right here I have an isosceles right triangle whose legs are 3 each, and whose hypotenuse is 3 times the square root of 2. Here I have an isosceles right triangle whose legs are 10 each, and its hypotenuse is 10 times the square root of 2. Let me just go back a screen, right? Here I had an isosceles right triangle where each side was 5, and its hypotenuse was 5 times the square root of 2, right? So, what are we really seeing here? You know, let's take a look at the most general case, exercise number 3. Given the 45-45 right triangle shown with legs of length s, do the following. Letter A. Using the Pythagorean theorem, show that the hypotenuse must be equal to s times the square root of 2. So in other words, I claim that in every isosceles right triangle, the hypotenuse will always be whatever the leg length is times the square root of 2. Let's do this together, okay? Let's prove it, right? The Pythagorean theorem will say a squared plus b squared equals c squared, right? We have s squared plus s squared is equal to c squared. S squared plus s squared is 2s squared is equal to c squared. That means c must be the square root of 2 times s squared. So c would be the square root of s squared times the square root of 2. And the square root of s squared will simply be s, and the square root of 2 we will leave alone. And there we go. In every situation where we have an isosceles right triangle, the hypotenuse is always going to be equal to the square root of 2 times the side lengths. Or if you like, the side lengths are always going to be the hypotenuse divided by the square root of 2. Now what's really cool, let's make a connection to right triangle trig, because that's, you know, kind of why it's in this unit. Let's take a look at letter B. Using A, state the value of both the sine and the cosine of 45 degrees. All right, well let's just hone in on this particular 45. We could do either one of them, it wouldn't matter, right? Let's take a look at the sine ratio, right? The sine is opposite over hypotenuse, right? So the sine of 45 degrees would be the side opposite, which is s, over the hypotenuse, which would be s times the square root of 2. All right, and you might be like, well, that looks like it depends on s. But it doesn't, right? Because the s's would just cancel, leaving me 1's in both cases, and that would be the sine of 45 degrees is 1 over the square root of 2. Not the prettiest number, mind you, but it's a number. And the cosine is going to be exactly the same. Why? Well, the cosine is going to be the same because the adjacent side is also s. So the cosine of 45 degrees is also s divided by s times the square root of 2. Those cancel, leaving me with 1's, also 1 root 2. All right, now we want to verify this using our calculator, so I'm going to go grab my calculator really quick. Let me just bring this thing up. Okay, and I actually want to make this on like its full size. I want you to be able to really see this, right? Now, what I just found was that the cosine and the sine of 45 degrees was 1 divided by the square root of 2. All right, so let's just take a look at what that is as a decimal, right? Whoops, 1 divided by the square root of 2. Or if you like, if you really want it as a fraction, let me put it in fraction notation. Why am I having that problem? 1, there we go, square root of 2. Get all the way out, enter, ugly, not the nicest number, right? That's what we found when we just went through and did adjacent divided by hypotenuse and opposite divided by hypotenuse. Now let's ask our calculator for what the sine of 45 degrees is and what the cosine of 45 degrees is. And they're all the same. And of course they have to be the same. The calculator is just storing this ratio inside of it, right, for the 45-degree angle. All right? By the way, just to finish it off, not that this was part of this, but just for a moment, tangent of 45, that's just equal to 1, right? And that's because the opposite and the adjacent in a 45-45 right triangle are the same size, right? That's the point. It's an isosceles right triangle, so opposite divided by adjacent, no matter how big they are equal to 1. All right, but it's kind of interesting, right? So this gives you a sense for where these two numbers come from in terms of the calculator. They just come from the expression 1 divided by the square root of 2. All right, let's go back in and let's start taking a look at our second, well, actually, no, we have one more problem on this. Let's take a look at exercise number 4. A square has a perimeter equal to 32 centimeters. What is the length of its diagonal in centimeters? All right, pause the video now and see if you can figure out this answer. All right, well, we're talking about a square, so let me just draw that really quick. All right, with a perimeter equal to 32, so 32 divided by 4 is going to be 8. That means I've got a square that's 8 by 8 by 8 by 8, okay? And I want to know the length of one of its diagonals. Well, that's a piece of cake. Now, I'm not huge on memorizing stuff, okay? But this is a nice pattern to know, right? I've got a 45-45 right triangle here, and likewise one right up here. Now, I could totally use the Pythagorean theorem to figure out the length of that diagonal, and you should definitely do that if you need to do it. But sort of the point of this lesson is knowing that when we have a 45-45 right triangle, that hypotenuse will always be the side length times the square root of 2. So even without using the Pythagorean theorem, I can figure out the diagonal has a length of 8 root 2. And I should put some units on here. Centimeters, right? Because the side lengths are in terms of centimeters, certainly the diagonal length will also be in terms of centimeters. Okay, now let's move on to our second one. Now our second special right triangle comes from examining properties of an equilateral triangle, strangely enough. So let's take a look at an equilateral triangle in exercise number 5. Equilateral triangle ABC is shown with side lengths of 10. The altitude from A to BC has been drawn, forming congruent right triangles ACD and ABD. It is these triangles we want to examine. So let's talk about this a little bit. All right, so the next special right triangle is going to come from basically splitting an equilateral triangle in half. Splitting it in half, right? And what we're getting is we're getting two right triangles that are identical, so we're only going to be thinking about one of them here. But let's think about the one on the left. So, letter A. Sketch triangle ACD to the right and fill in the measures of its angles. Okay, great. Why don't you go ahead and do that? Sketch triangle ACD right here, I've given you space, and fill in the measures of its angles. All right, well, one thing that you have to know is that in all equilateral triangles, the angles, all three angles, are equal, and they're all equal to 60 degrees. So when I take that half triangle out, right, and I've got that 90 degrees, this is still 60 degrees, but this has now become 30 degrees. Okay, so this is my CDA. Ah, there we go. Okay, great. Let's take a look at letter B. What must be the length of CD? Label on the diagram. All right, so I claim that I know what that length is. Go ahead and figure that out. Pause the video now. Now, I'm not trying to use anything fancy here, right? I just want to know that that's 5. And of course that's 10. But of course that's 5 because what I've done is I've taken my equilateral triangle and I've just split it in half. So this base that's 10 units long here becomes 5 here. Letter C. Use the Pythagorean theorem to find the length of AD. Label it as well on the diagram. And I really should have said in simplest radical form, okay? But why don't you go ahead and use the Pythagorean theorem. This time we're not solving for the hypotenuse, so it takes a little bit more work, right? But figure out what that length is. Pause the video now. All right, well, maybe I'll call it A. I don't know, doesn't really matter, right? And I'll have A squared plus 5 squared is equal to, is equal to 10 squared. That's going to give me A squared plus 25 is equal to 100. Subtract 25 from both sides. Move this out of the way. I'll get A squared is equal to 75. Come on. A is equal to the square root of 75, which I can then break into the square root of 25 times the square root of 3, and A is equal to 5 root 3. So that's right here. Right? That's 5, that's 10, and that is 5 root 3. I also want to put it up here. All right. Because what I'm really looking at now is what's known as a 30-60 right triangle. Again, we're naming these based on the two acute angles, right? The 45-45 right triangle is the isosceles right triangle where the two acute angles are equal. Here we've got a 30-60 right triangle. Sometimes they're referred to 30-60-90 triangles as opposed to 30-60 right triangles. And notice, right, in this situation, right, the side length that is half of the hypotenuse is across from the 30-degree angle, and then that obnoxious one that's got a root 3 in it, that's across from the 60-degree angle. Okay, so let's keep working with our 30-60 right triangles. When we split an equilateral triangle, let me move this out of the way. When we split an equilateral triangle using one of the altitudes, it creates two right triangles with acute angles of 30 and 60 degrees, right? The 60-degree angle is there because it was there in the equilateral triangle. The 30-degree angle is there because we sliced one of the 60-degree angles in half. So let's play around with another 30-60 right triangle to see if we can develop patterns the way that we got that pattern with the isosceles right triangle. Exercise number 6. For the 30-60 right triangle, EFG shown below, do the following. Letter A. Which leg length is equal to 4? Fill it in on the diagram. So I claim, right, that one of these two leg lengths is equal to 4. Which one is it? And see if you can think about it by thinking, if I drew in the other half of the equilateral triangle, where would it be? It would either be, right out here, or it would be down here. Think about that for a moment. Pause the video now. All right, well, the length that's going to be 4 is going to be right here, right? And again, the reason for that is that that equilateral triangle is right here, right? So the side length that is opposite, so in fact, I'm going to just say EG is equal to 4. The side length that is opposite the 30-degree angle will always be 1/2 of the hypotenuse, always. And that is simply because it is half of that equilateral triangle side length. That's it. Now let's look at letter B. Use the Pythagorean theorem to find the length of the other leg. Compare your answer to your result from exercise number 5 to see a pattern. All right, so now what I'd like you to do is figure out what this length is using the Pythagorean theorem. Pause the video now and see what you get. All right, let's do it. So again, maybe I'll call this A, right? And I'll get A squared plus 4 squared is equal to 8 squared. A squared plus 16 is equal to 64. Subtract 16 from both sides. A squared is equal to 48. Take the square root of both sides. Biggest perfect square that goes into 48 is 16, and it goes in 3 times. So A is 4 times the square root of 3. So let's get all those labeled. All right, that's it. Now, when it says compare your answer to your results from exercise 5 to see a pattern, right? So one thing we want to note right away. The side length that is opposite the 30-degree angle in a 30-60 right triangle is half of the hypotenuse. And the longer side appears to be the shorter side times root 3, at least in this case. Let's go back to the previous one. In this one, again, the side length that is opposite the 30-degree angle is half of the hypotenuse, and the longer side is that shorter side times root 3. And that is, in fact, the pattern in a 30-60 right triangle. So let's talk about the patterns. Special right triangle patterns. The 45-45 right triangle, right, what we've got is 2 sides that are the same length, and the hypotenuse is that side length times root 2. Let's pop out for a second, though, and talk about the more complicated one, the 30-60 right triangle. All right. Now, in this right triangle, what we've got, right, is we've got that hypotenuse, let me call it H. We've got the shorter of the 2 sides, which is the side across from the 30-degree angle, and that is simply 1/2 of the hypotenuse. Now, the longer side, I'm saying, is root 3 over 2 times the hypotenuse, but really, what this is it's 1/2 of the hypotenuse times root 3. In other words, it's this that's then being multiplied by root 3, which is what we saw, but kind of the way that it's typically phrased is root 3 divided by 2 times the hypotenuse. All right. Now, what these patterns allow us to do is very, very quickly fill in the lengths of sides of right triangles that are either 45-45 or 30-60. Let's take a look at exercise number 7. Fill in the missing sides of each right triangle shown below. All right, so let's do the 30-60, right? So in this 30-60 right triangle, I've got my hypotenuse, and it's equal to 40. What I know from my patterns is that the shorter side, the side opposite the 30-degree angle, is simply going to be half of that 40. It's 20, right? And again, that's simply because this is literally, let's say, the upper half of some equilateral triangle like that. All right, the longer side is going to be the shorter side times the square root of 3. Very fast. Now, again, just like before, right, you could certainly, if you have the 40 and the 20, you could use the Pythagorean theorem to figure out the 20 times root 3. All right, let's take a look at letter B, where we've got a 45-45 right triangle. Now, in this situation, we don't know the hypotenuse, but we know one of the legs, which is 15. Now, what we know is that the other leg also has to be 15 because it's an isosceles triangle. And sides that are opposite equal angles in a triangle are equal in length. And our pattern now tells us that the hypotenuse, right, is going to be the side lengths times the square root of 2. So this is going to be 15 times the square root of 2. Okay. What I'd like you to do is pause the video and see if you can fill in the lengths in letter C. All right, well, in letter C, we've got our 30-60 right triangle again, but this time I've given you the length of the shorter leg as opposed to the length of the hypotenuse. Now, we know that the length of the shorter leg, the length that's opposite the 30-degree angle, is 1/2 of the hypotenuse length, which means, of course, that the hypotenuse length is twice the length of the shortest side, so that's going to be 24. All right. We also know that the longer leg is going to be the shorter leg times the square root of 3. So that is going to be 12 times the square root of 3. And that's it. So let's summarize. Now, there are a lot of right triangles out there with all sorts of different acute angles, okay? But the two that we consider special for a variety of reasons, right, are the 45-45 right triangle, aka the isosceles right triangle, and the 30-60 right triangle, aka half of an equilateral triangle. Both of these two right triangles come up a lot, both in right triangle work and in trigonometry, especially as you move to higher level trig in Algebra 2. Knowing how the side lengths relate to each other, i.e. in a isosceles right triangle, the hypotenuse is the leg length times the square root of 2. And in the 30-60 right triangle, the idea that the shorter leg is half of the hypotenuse and the longer leg is the shorter leg times the square root of 3, those patterns are helpful. They're helpful because anytime these two triangles come up, you can then very quickly find their side lengths by using the patterns. You can also use the Pythagorean theorem. Let's give a nod to that, right? All of these patterns came from the Pythagorean theorem, ultimately. But if you've got them memorized, they make solving the problems much, much faster, okay? And we will see them on and off in the rest of this course. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.